What we want to do now is to create a function that produces the Fibonacci sequence. In particular, we will learn about recurrence, and we will learn also a few more tricks about how to use the Magma language, the Magma syntax. Here's quite literally a textbook example on how to write the Fibonacci sequence. So this is actually from the Magma help book. So we write this function, textbook Fibonacci. This is created in the short form. It takes a single input n, and then what it does is, well, the first thing is a comparison operator. It checks whether or not n is less than or equal to 2. And then there's select. Here's what select does. You have to give it a boolean on the left. For example, you can give it a literal boolean, true, and then write select. And then it will execute the next statement if the boolean was true. So, and then if you have else next to it, then it will enter into this clause only if the boolean is false. And you have to end this creation with a semicolon again. For example, here true will select the first statement, execute it, and then we will quit this line. It will not enter into the else clause. If the boolean was false, we will enter into this other clause and we will skip the first clause. For example, let's try it. As you can see, it executed the first line, which was just a string, and it outputs it. If I change the boolean to false, then it will just write no here. So it's just executed the second statement. Of course, I don't have to just write down a boolean here. I can write down something that creates a boolean. For example, 3 is less than 2. So this will produce a check. It will check if 3 is less than 2, and this will be a boolean false. Therefore, we will get no. If instead I write 1 less than 2, then I will enter into the first clause. We now know what the function does at first. It checks if n is less than or equal to 2 here. So this is a boolean. If this is true, then the function outputs 1. So let's agree that we will use this function for values at least 1. Therefore, for n equals 1, n equals 2, the function will return 1. Sounds reasonable. That's how the Fibonacci sequence begins. Afterwards, it looks like it's referencing itself and summing up its two previous values. Since we know what a Fibonacci sequence does, we can guess that's what's happening here. And indeed, this double dollar symbol is for a function to reference itself, to call itself. And since this function creation uses a format where the function does not know its name, this is the only way the function can call itself. And what it does is clear. So it evaluates itself at n-1, adds it to its value at n-2, and then returns it. So for n greater than 2, this is what's going to happen. And we can check whether that works. So textbook Fibonacci 1 is 1, 2 is 2, this is 2, looking good. Well, let's do more of them all at once. So I'm going to write a sequence. Okay, so the first 20 terms of the Fibonacci sequence, it looks about right. There's a certain elegance to writing the Fibonacci sequence like this. However, it's not very efficient. So let's see how long it's taking and where it chokes. So let me write a for loop. So what this for loop does for 1 through 36 is that first it will output n, and then it will output the textbook Fibonacci n. Let's copy paste. And you see it has already slowed down at the 34th element. And it took quite a while for it to finish at the 36th. We can even time how long it takes. For example, we can write time textbook Fibonacci. The 35th, I think, was taking long enough. Let's see how long it takes. It took about 2 seconds. In fact, if you think about how this function was created, this textbook Fibonacci 35 calls itself, so calls the function textbook Fibonacci about this many times. So that's about a 10 million. and that's why it's slowing down. Here's what I'm going to do. I'm going to create two numbers, a equals 1, b equals 1. So these are my initial conditions for the Fibonacci sequence. And for its instructive value, here's what I'm going to do. I'm going to create a function that takes two Fibonacci numbers, let's say fk and fk plus 1, and returns the next two. So fk plus 1, fk plus 2. That's what I have in mind. Let's call this function next. So what this function does is that it returns the second value and then returns the sum of these values. So this is clearly a fundamental operation for the Fibonacci sequence. Let's go back. I'm going to repeat this now. For k in 1 through n, do ab equals next ab and 4, and then return a. Let's copy this and then paste it here. This is almost doing what we want, but not quite, because the index is off. So let's go back and correct the index. What I'm going to do is start with 0 here, and then we will be on track. So let's copy paste. Let's see what Fibonacci does now. And now it looks correct. 1, 1, 2, 3, 5, 8. The good thing about this new Fibonacci function is that it should be much faster. Let's try it out. Last time it took about 2 seconds to compute Fibonacci 35. Now, well, it doesn't even register. Let's increase to 100. Still doesn't register. Can we do 1000? Let's try much larger numbers. Let's say 10 to the 6. So now it took about 3 seconds and we got the millionth Fibonacci number here. We can see how long this Fibonacci sequence is, so how many digits it takes. We can do, for example, the following. F million, so 10 to the 6. It's going to take 3 seconds. Now what I want to do is to convert this into a string. One way to do this is to say sprint. So sprint is string print, and it will convert whatever you give it into a string. But I want to see the length, and the length you see with this hashtag. And there you go. So the millionth Fibonacci number has 208,988 digits. Let's do a slight variation on our function. What I'm going to do is to use the explode function. So this is very useful. So this doesn't give an advantage in terms of time, but nevertheless, it's very efficient in terms of writing it. So I've written a function Fibonacci 2. My initial conditions are just as before, but this time I do not declare a new function to do this shifting of operation. Instead, I just enter into my for loop. And what I do is that inside a sequence, I create b and a plus b. Now it's rather cumbersome to assign the entries of a sequence into then a sequence of names. What you do is to use explode. Let's try what explode does. If you give it a sequence, it will return the entries of the sequence one by one. Therefore, you can then assign variables to them. That's what I'm doing. I'm assigning a, well, in this case to b, and b to a plus b. And this too is very convenient. It will do what we want. Let's see how long does Fibonacci to 1,000,000 take. Let's give it a name again. So it took this time a little over 3 seconds. So in fact, it was even less efficient than the one before. Well, presumably, I mean, it's just very little time difference, but it's certainly easier to write. While checking that at least the number of digits of this millionth Fibonacci is the same as the other millionth Fibonacci number, and as they should, they agree. Now for our last example, I want to introduce a new functionality of function creation. You can create functions with parameters. So parameters, unlike, let's say, inputs or variables, are not meant to be changed all the time. So they're kind of fixed. Let me show you how you can use them. I just copy pasted our function from before. Let's change it to Fibonacci v. I'm going to create a parameter. So here's how you create one. I created another variable. I called this variable verbose. I could have called it anything else. I could have called it XXX, but let's call it verbose for now. And then unlike other inputs, this has a built-in value, and its built-in value right now is false. And afterwards, the function right now doesn't use verbose, but what I want to do is to print the current value of a if you have verbosity set to true. Let's see how this works. So if I just call Fibonacci v10, nothing happens, and this is the default behavior of the function that I had in mind. But now there is this small variation that I can do. I just write verbose equals true, and now it will output all intermediate values that it acquires. So to be clear, so maybe this is a little clearer. So the last 55 here was the return value of the function. So now I assign it to F10, so it's not output here. And instead I see all the intermediate values of the Fibonacci sequence. Just to make this clear, I could have written here XXX and here XXX. And now this would also work. But now I have to be careful how I call the function. Here I need to write XXX. Now the same behavior. Of course, you should use names that signify what kind of behavior is supposed to be expected. You can have many more parameters, not just one. So I've used only one here. And in principle, you use them to create a standard version of the function. And then this standard version can be changed by altering these parameters, just like we did by setting the verbosity. Now let me demonstrate how you can create and use another variable very quickly. For example, I can shift my output by this meaning of life, which I created to be 42. Now I copy paste this here, and then Fibonacci v10 will give me 97 instead of 55. But we can set the verbosity to see the true values of the Fibonacci sequences, so that I see that I really added 42 to the final answer. That concludes our lecture. In addition to basic function creation, we've learned about recursion, self-reference of functions using this $$ symbol. We've learned about how to use select, a very useful functionality. And then we've learned, and we've saw that, of course, recursions can be expensive. So we've created our own function. And to see how long it takes, we use the timing function. We used this sprint, again, very, very helpful function, hashtag to count the number of letters, and then we used explode. Afterwards, we looked at these parameters, and here I created the parameters verbose and meaning of life. Now, you should be ready to study the forest fire example in this examples book that I linked below. Here, there are some things that we might not have covered, for example, the function floor, but you can guess what it means, and you can always use the question mark to read about it. And then there are certain things which you can guess what they're doing. For example, here a function is created and then immediately used by evaluating it here on this tube fair. Once you feel comfortable with this example, then you can implement your own game of life inside of Magma. Alright, so today was in preparation for the kind of functions that we're going to write next week, when there will be some algebraic geometry involved. And in the next lecture on Wednesday, we're going to be covering Grassmannians, again in preparation for the following Monday. See you then.